I'm sorry to tell you, but Harold isn't better yet. He's still in the hospital, although he's doing well. He appreciates the cards and flowers you folks have been sending. All right, because he didn't get better fast enough, the hospital's made a couple of changes. First of all, they've shifted from the cylindrical container for his medication to this nifty conical container, where the top has a radius of 3 centimeters and the container is 6 centimeters tall. Now, of course, at every moment in time, we'll have a little miniature cone of medication inside of that conical container. But the difference here is that if the volume is changing at a constant rate, the height's actually going to be dropping at a changing rate. Because when it was very full, okay, in order for it to drop this amount, look at how much volume had to leave that container. But down here, a similar change in height corresponds to a much smaller volume, simply because we're looking at a smaller cross-sectional circle there. Okay, so they've changed to the conical container. They've also upped the rate at which they're pumping medication into Dear Harold. It is now 0.004 cubic centimeters per second. And we are asked how fast the level of medicine is dropping when the nifty conical container is filled to a height of 3 centimeters. Now, in the last problem, when we had a cylindrical container, I didn't have to tell you what the height was at the time that we cared about, and that's simply because the height was dropping at a constant rate. Here, since it's dropping at a changing rate, I had to specify the time that we care about. I didn't specify that by naming the time. I specified that by naming the height of the medication at that time. Okay, so here we've got a cone, and it looks like we're going to care about the volume of the cone, because again, this is a rate of change in volume. It's the change in the volume of that cone of medication that we have. So the volume of a cone is 1/3 pi r squared times h. Okay. Basically what this says is that if I had a cylinder with the same radius and height, I could fit 3 of those cones in there. Okay, so add that to the formulas that you should be familiar with if you weren't already. Okay, so that's going to be the relationship between the things that are changing. Volume is 1/3 pi r squared times h. Now here, you'll notice I have 1, 2, 3 non-Greek letters. Pi is a letter, it's a Greek letter. I know that represents a number. Okay. V is the volume, that's changing, so that's a function of time. H is the height, that's changing, so that's a function of time. And R is the radius, and that's changing, so that's a function of time. R and H do not refer to the radius and the height of the container. That's staying fixed. They refer to the radius and the height of the miniature cone of medication inside that container. And as some of that medication seeps into Harold, the height's dropping and the radius is shrinking. So I have 3 functions of time. I'm only told 1 rate of change here. So if you remember when we listed the steps, I said the issue hadn't come up yet, but when you get your equation giving you the relationship between your functions of time, you want to have it so that you know all but one of the derivatives. Now I know h prime is what I'm solving for. V prime I was given, I don't know r prime. I also don't care what r prime is. So if I don't know and don't care, I want to get rid of those r's. So what I want to do is see if there's some additional relationship between these variables so that I can express r in terms of the others. Now, if I look here, if I just look at a cross-section of things, I can see that little triangle in there. So here's the cross-sectional triangle of medication inside of that cross-sectional triangle, which is the container. I know for the container this is 3 and this is 6. I'm going to just draw a copy of that little triangular cross-section of the medication, this would be the height, this would be the radius for that. But these are similar triangles. Okay? Similar triangles means they're exactly the same shape, even though they're different sizes. So the three angles are the same. Okay? That angle's the same because it's literally at the same location. This is a right angle, this is a right angle, so this angle and this angle are also the same. Okay? So if they're similar triangles, they're exactly the same shape, their sides are proportional. So I can set up a proportion. I can say 3 is to R as 6 is to H. The radius here corresponds to the radius here, the same way the height here corresponds to the height here. And if I cross multiply, that's going to give me 3H equals 6R. Now what I'm going to do is I'm going to solve for R, and that reduces, R is just half of H. I can see, I have that relationship here. The radius was half the height. That relationship is going to stay constant even as R and H both get smaller. So what I'm going to do is simply replace R with H over 2. Now I just have two functions of time. Volume, whose rate of change I know, and height, whose rate of change I want to know. Okay. Now I can simplify this a little bit. This is 1/3 pi times h squared over 4, square the top and the bottom, and then times that other h. So the volume is pi over 12 h cubed. Excellent. Now, I could have done this work after I took the derivative, but notice here, I'm multiplying together two functions of time. I would have to use product rule. Here, I've just got h cubed. Okay. So this is a lot nicer, and I'm going to have to do this work at some point anyway, because I don't know r prime. Okay. So I'm going to just indicate that h is the inside part in a function composition there. And now let's take the derivative with respect to time of both sides. Okay, derivative of v is just v prime. Nothing complicated there. If I have a name for the function, when I take the derivative, I just name the derivative. Constant multiple rule, that's a 12, sorry. Constant multiple rule says I'm going to get pi over 12, and then power rule times 3h squared, chain rule times h prime. So let's see, I can cancel the 3 and the 12. So v prime is pi over 4 h squared h prime. Excellent. We wanted to know h prime. We need to plug in for v prime and for h. V prime, 0.004 is the absolute value. And again, in this problem, the volume of medication in the container is decreasing. So that's going to be negative 0.004. And that's equal to pi over 4 times, we cared how fast this was dropping when the container was filled to a height of 3. So that's the height at the moment in time we care about. We've got to square that. And then times h prime. So negative 0.004 equals 9 pi over 4 h prime. H prime will equal negative 0.004 over 1 times 4 over 9 pi. So we want to simplify that and then answer the question in words. All right, that's going to be negative 0.016 over 9 pi. Again, I don't want to mix fractions and decimals, so I'm just going to multiply by 1 in the form of 1,000 thousandths. That's going to give me negative 16 over 9,000 pi. Okay, so that's h prime. That's the math answer. And then I can say the level is dropping. And the word dropping accounts for that negative sign at a rate of Just give the absolute value, 16 over 9,000 pi, and then I want to state the units. So if this was h prime, what were the units for the height? Those were just centimeters, and the units for time were seconds. I am pleased to report that this new course of medication is working very well. Harold has a very positive prognosis.